All right, so we're going to look here just at this doing Newman projections. And for the most part, just know and understand the basics of different conformations. So for this, I just have simple butane here. And basically what I want you to do is view this along the bond in red, because technically you could view this across any of those bonds. Okay, but if we do this bond in red here, for the Newman projection, remember that this dot will be my front carbon. This will be my back carbon. Okay, so if I draw this as a Newman projection, okay, we have this. All right, so if we look at the front carbon, what is on that front carbon? We have a methyl group and 2 hydrogen. Okay, so draw those in. I'll just put the methyl up here, and then draw them basically spaced evenly around the circle, we'll say. The H and the H. Okay, then on the back carbon, that has 2 hydrogen and a methyl. All right, so let's start by drawing the most stable conformer of this, where you want the biggest groups anti. So I'm going to put this CH3 anti to the other CH3. So there's that one. There's that one. And then again, space those hydrogen around equally. Okay, so in this case, this is a staggered anti-conformation. Okay, now you can rotate this in 60-degree increments, but I'll just show you a couple of other conformations. Okay, so one, let's just rotate these front 3 groups around just counterclockwise. Okay, this one here is still staggered. Okay, but this has these 2 methyl groups nearby, and those kind of interact right there. So this is called the gauche conformation. And then let's just say I move this front carbon around such that the methyl groups are in front of one another, the hydrogens are also in front of one another. Okay, it'll look something like this, and this is an eclipsed conformation. So stability-wise, the eclipsed is the worst, and it's the most, I'll just say the most worst, if you have the two methyls in front of one another. And then the staggered is going to be a little bit more stable, and then if you have the staggered where they're anti, that'll be the most stable. Okay, so that's one thing you want to be able to do is just kind of look for the most stable Newman projection. Okay, and look for big groups. So things like methyl, ethyl, it can get even bigger, like isopropyl, tert-butyl. If you happen to see a halogen, halogens tend to be, just kind of simplify it and think halogens are about the same size as a methyl. Not quite as big, but bigger than hydrogens. Yeah?
Are we going to know the energy values?
Yeah. All right, so let's take a look at the chair conformation. Again, I'll just kind of point out halogens aren't as big as methyl groups. Okay, so here we have two chair conformations. And then in terms of stereochemistry, what if you're asked what's the relationship between these two? Okay, this is something that, just looking at those two, it's really hard to tell. Are they identical enantiomers or diastereomers? So anytime, I would work a problem like this. If you need to figure out a relationship between two chairs, draw them as flat structures. All right. Draw a six-membered ring. Okay, pick a carbon as a reference point, and that's the one we'll do with the fluorine. The fluorine is pointed upwards, put it on a wedge. Okay, number around. Well, it probably would have been easier to have done counterclockwise, but I did clockwise. So if I numbered clockwise on this chair, number the ring below clockwise. All right, the other group is at 5. It's a methyl group. That one is pointed downward, so put that on a dash. Like that. All right, let's do the same thing with this one. There's my reference point with the fluorine. Draw it in as a wedge. Clockwise, number to 3. The methyl is down. So I'll put it back. Okay, so they're still not quite easy to tell, but if we take this and think about a potential mirror image, what if I just spin this around so that this green dot mirrors that green dot? All right, I'm really just like turning this in the page. Okay, we do that, and you can see that those two are mirror image structures, so those are enantiomers. Okay, if you drew this and you could spin it around or flip it so everything lines up, then they would have been identical. All right, so the second question is just which chair is more stable. Okay, we're comparing these two. One has an axial fluorine and an equatorial methyl. The other has an axial methyl and equatorial fluorine. Okay, well, we know that methyl is the larger group, and having things equatorial is more stable than axial. So it's best to have the bigger group equatorial if possible, so the first chair is the most stable. Okay, likewise, if you had to assign RRS configuration to a group on a chair, I think it's probably easier to draw it in this dash wedge form and work from that. All right, any questions? Yep.
Have to do that, or can you just say in the first chair the methyl is equatorial and then it's axial, and then the same way for how that F is axial to equatorial, and can you just be like that's enantiomers or not?
No. So be careful with that because depending on where they're placed, that could end up being an identical compound. Any other questions? Okay. All right. This something that we've hit on several times this semester, and this is going to be important for the final. So make sure you know that you get increased stability with substitution. Just do a couple. Oops. Okay, now this is where, though, if they're drawn in kind of this condensed form, just make sure you can still, read the alkene structure. And basically, this first one is unsubstituted, so that should be pretty straightforward. But the second one, just know that on this alkene carbon, the hydrogen's bonded to it, the methyl's bonded to it. So that's more stable because that's monosubstituted. This next one, this should be hard to see, CH3, right? But if you have two CH3s in parentheses, that means both of those are connected to this carbon. And then you have on the other carbon, the H and the CH3. So this one is tri-substituted. Right? Then also, just don't forget what we covered this semester with conjugation. Conjugation is a good thing. It increases the stability of alkenes. So if we add double bonds in conjugation, you're becoming more and more stable. Yep.
Isn't like trans more stable than cis? And if so, like, is there any way to tell with the condensed structure, like which one's trans and which one's cis?
No. So if you're given a condensed structure, you won't know. Like, you can't be expected to know if it's cis or trans. Any other questions here? All right, so just remember, knowing alkene stability is going to be important for probably a few different questions. All right, so let's spend some time on reactions. I have a few different things I want to show you and talk about. First thing is something I probably should do more is use deuterium. So deuterium is just essentially a different form of hydrogen. It has one additional neutron, but if you see a deuterium, it reacts identically to how hydrogen would react. So it just gives you a different atom instead of the hydrogen. Okay, so on this first one, if you see D2 palladium on carbon, right? Well, I would hope you know what H2 does. It adds hydrogen syn across the double bond. Okay, but if you add D2, you're adding deuterium. Okay, why is this used? Well, it gives you a way to kind of analyze reactions for stereochemical outcomes and some other mechanistic insights. But if you just did this reaction with hydrogen, you wouldn't know if the hydrogen necessarily added cis or trans by looking at the product. But if we use deuterium, we can see that both deuteriums added in the same direction. All right, so this one you get 2 chiral centers, but also you should know because there is a plane of symmetry cutting through this molecule's achiral. All right, remember, those are called meso compounds. If you have a molecule that's achiral but has chiral centers. And I think once or twice I used deuterium this semester just to show you how it can be used to analyze a mechanism. So for example, in this reaction, knowing where the the D3O plus is involved. Okay, so for this, here the methoxide adds and opens the epoxide. All right, then in step 2, you add instead of H3O plus, D3O plus. All right, but that's just, instead of a proton, you're adding D plus.
It goes from pentene to pentane to hexane.
Little magic. There. Okay, that's better. All right, so from there, just now protonate with the deuterium. Like that. Yeah.
So say there was a methyl on like one side of the oxygen, would it add to the more substituted side? Like the more topical?
So if you had a methyl, this. If you use, in step one, if it's a nucleophile, it'll add there to the less substituted side. If you use acidic conditions, something like sulfuric acid, or maybe just H plus and methanol. The OCH3 is your nucleophilic group, but the acidity changes the regioselectivity of the reaction, and this group will add to the more substituted carbon. Yeah.
If you were doing it with stereochem, would they add trans and there would be an enantiomer? Or
Yes, so if, let's say, just in this first reaction, let's say I have this epoxide as a wedge, right? This methoxide would add from the back side of that wedge, so it would be back. This would still be out. And then in the product, you would have back and out. But you would have to consider addition to the other carbon, because in this case you can't decide between sides because one's not more substituted than the other. So then if this added on the other epoxide carbon, you could get that, and those are enantiomers. Any other questions here? Okay. Let's see. All right, another thing with reactions, and this is something where, if I had to say the two hardest parts of the exam, one is their use of condensed structures, but I will say the exam you're in that regard. Second thing is just terminology. Sometimes they use terminology that's a little different than what I would use. So one thing just to keep in mind is the term ionization. Okay, that's basically saying what I call loss of a leaving group. So here's a sample question: which one will undergo ionization at the fastest rate? Okay, so we kind of talked about something very similar earlier, but C and D are tertiary, and ionization, or loss of the leaving group, It's basically just saying you're breaking that bond to give you the carbocation and the chloride anion. So that's where the ionization term comes from. Okay, and then this one, both give you a tertiary carbocation compared to secondary in A and B. So then your second analysis is just a leaving group, and like we talked about earlier, bromine is better than chlorine as a leaving group because it's larger. So that would be D. Any questions on that? All right, another thing you'll remember from organic, the acetylide ion. That is the triple bond CH. Okay, so we want to make trans-2-butene starting with acetylene. Right, so there's trans-2-butene. The 2 carbons from the pi bond those come from the 2 carbons in acetylene. All right. These protons are acidic, so you can treat them with a base. The most common is something like, let's do it in steps, NaNH2. Right, that will deprotonate acetylene. To give you this acetylide ion. From there, now you can add whatever carbon chain you want. All right, in this case, I'm just going to add a methyl and then another methyl. So you just need a methyl halide. Just use iodomethane. And I methylate one of those positions. Okay, so then to do the other side, you just need, since it's an identical group, you just need a second round of this. Okay, don't get thrown off if they use a different counter cation, maybe KNH2. Or a different halide like CH3Br. Nonetheless, we'll put a methyl group on the other side. Okay, so we now have 2-butyne. We need the double bond, and there's 2 ways to reduce this alkyne. And this one for the trans, you take solid sodium, put that in with liquid ammonia. This is done at low temperature, but I think somebody showed where it didn't include the low temperature. But still, the low temperature, I guess, makes it better, but I don't know why. Like, it's one of those deals where sometimes we write the temperature, sometimes we don't. Every reaction is carried out at some temperature. A lot of times just Don't let the temperature part throw you off. So what that does, thanks to the hydrogen in the ammonia, that gives you the trans product. Okay, if you want the cis product, you use hydrogen and Lindlar's catalyst, which is a deactivated palladium catalyst. You get that. If you were to just use our standard hydrogen reducing agent, hydrogen with palladium, that will reduce this triple bond totally to a single bond. So you just end up with butane. All right, so just remember this acetylide ion is a good way to add carbons.
Really, my phone's on silent.
Just bad luck. All right, so any questions on this? All right, another term, which this is one that should be familiar, we used it in Organic 1, that is solvolysis. Okay, but basically solvolysis is your nucleophile as also the solvent, and this is always dealing with an SN1 reaction. Okay, so what's the first step of SN1? Well, we'll stick with the ACS terms and do an ionization. All right, from there, now we're going to use, this is ethanol as the nucleophile. Draw in the lone pairs. That O attacks the carbocation. Okay, it still has the proton on it at first, and then we just need to take that proton off. And this reaction is flooded with ethanol, so we can use that as a base, or a lot of times you just use B. Take the proton off. There's your product. Any questions on that? All right, one that I don't think I put in here, but it just popped in my mind that I want to mention. Because it's something you know, but you may not recognize. Everybody get that? Okay. Okay, if you see anything like And it takes, you have to look kind of carefully to spot it. A carboxylic acid is CO2H. If you see a CO3H, that's basically what MCPBA is. So MCPBA, instead of a carboxylic acid, it's this peroxy acid, right? And they tend to use the reagent written out like this instead of writing MCPBA. So if you spot that CO3H, what should immediately pop into your mind is epoxide. So if you do that, what that does is it epoxidizes double bonds. Right, just adding that oxygen across. Any questions on that? Okay. All right, so one more reaction I want to talk about. Which is one, really we should probably, it's like when we start reactions with all the alkene reactions, people tend to get overwhelmed. This is an important reaction. It's the ozonolysis. And it's also a pretty easy reaction to predict the products. Okay, what it does is uses ozone to cleave pi bonds, typically double bonds. Right? But predicting the products is super easy. What it does, it'll cleave all the double bonds in the molecule. Okay, this one only has one. And I'll go ahead and draw in this hydrogen just so we can keep track of everything. All right? Just split the double bond down the middle. Okay, and add an oxygen to each end. Okay, so you get double bond oxygens instead. So there's a product. There's a product. Any questions on that? Mm-hmm. DMS is it's dimethyl sulfide. What it is a reducing agent. It basically reacts with the intermediate that's formed. You get this ozonide intermediate, and it breaks it down and reduces the other oxygens that fall off.
Okay, what if it was just by itself? Will it not be
Any other questions on that?
Could it be something other than DMS instead?
There are different reducing agents. So really just look for the ozone. If you see ozone, and this holds true on like other exams like the DAT, if you see something like that, it's always going to cleave the alkene. All right, so just a little bit of spectroscopy and approximate proton NMR regions. Okay, now knowing these exact cutoffs really isn't all that useful. I would just say, know that, sp3 carbons are down here, or I should say up here in the upfilled region. They're your most upfilled protons. Then the allylics are a little higher than that. Then if you have a hydrogen on a carbon with electronegative atom, that becomes a little higher. Double bond hydrogens, aromatic carbons, or aromatic CHs, and then your carbonyl, like the aldehyde or carboxylic acid. Okay, so no, kind of general regions, but exact cutoffs probably aren't that important. Okay. And this table, you should all have some form of this. Okay, IR. So up here in the 3300 region, that is something H stretches. Usually OH or NHs. OHs are quite broad. NHs aren't quite as broad, but they're still fairly broadened. Also in that same region, you have the terminal alkyne CHs. But how can you tell the difference? Those are very sharp and narrow. Okay, then another good region to just keep in mind, or good number to keep in mind, I say just remember 3,000. Okay, because that's a great cutoff, because just below 3,000, sp3 hydrogens, just above, or sp2 hydrogens. Okay, and if you have trouble remembering the order, they go in order. sp3Hs, then a little higher than that are the sp2CHs, and then higher than that are the sp3CHs. Or, I'm sorry, sp. I don't like morning classes, I don't like night classes. Hard to please. All right. 10:30 is a perfect spot for me. So the next group, if you have a triple bond. So not all triple bonds are terminal, so you won't always see this terminal CH. But if you see the triple bond, that one's about 2100. I don't know, that's maybe not the most important one in this list. Absolutely make sure you always keep in mind the carbonyl. C double bond O is always around 1700. That's an important one. The double bond stretch is near that region, usually a little bit lower and not as intense. Okay, and the last one is, it's kind of a random group from the list, so take me putting that on here how you wish, but the CH3 bending just below 1400 is a good, we won't call that a stretch, we'll call it a good bend to know for IR. Okay. So, what? Not as sharp down toward the bottom. Yes. Yep.
What does CH3 bending mean exactly?
Well, so it's basically it tells you have a CH3 group. Okay. It's just the motion of the bond movement. Okay. So instead of stretching it out, it's bending. But what this is a good clue for is just a methyl group in the molecule. All right, so putting this data here, I think, into practice, I have an example. All right, so which one of the following is represented by this IR spectrum? Okay, one of the most important stretches in this spectrum is right here. This one's very strong and intense. It's about 1700. That's a C double bond O. Okay, also up here at 3300, you don't have any signs of an alcohol. You know, if you had an alcohol in here, you know, it would probably look something like that. You don't have that. So we can cross out D. I didn't really mean to have B and C being the same thing, but that's okay. Okay, the next thing we can spot is you have this stretch a little bit lower. That one's probably closer to 1650. Right? That is the CC double bond. So A, B, and C all have the CC double bond. Well, let's just get rid of C. So we're between A and B. Okay, between those, the big difference in this is using this 3000 as kind of a key. Okay, we have stuff below it that indicates CSP3H, stuff above it that indicates CSP2Hs. Okay, B only has sp2 carbons. Okay, so we've narrowed this all the way down to it has to be A.
Did you say there's stuff around 1400 making it like a methyl on that one side?
Yeah, it's so I was trying to count my numbers here to find it. So 19, 18, 17, 16. So here's the 1400 mark right there. And this one's not super clear to see, but and this is that methyl bending right there. So that could help you as opposed to, if the structure was this, which I bet this is what I was going to make C and screwed it up. But this one, you have the sp3s and the sp2CHs, but this one, no, that still would have the methyl bend. There. How's that? BR. Now this doesn't have a methyl group, so you wouldn't see that. What were you going to ask?
I was going to say, before you added the BR, would you have been able to tell, given the information between A and the one you just drew?
No, you couldn't. Yeah.
If you draw that line.
All right, so the first thing is you should be able to find your mass in your rightmost grouping of peaks. Okay, in that group, your tallest peak is your molecular ion. And that number tells you the mass of your molecule. Okay? And that's one piece of data you can use just comparing the mass to different structures. Okay, so obviously the bromine on a ring is going to have a higher mass than the chlorine. So you can easily differentiate those just by mass. But also, really important for halogens is the second peak. It's 2 mass units down from M+. It's M+2. Okay, and the ratio of M+ and M+2 tells you the difference between a chlorine and a bromine. So a bromine is 1:1. A chlorine is 3:1. So that'll help you differentiate those. Yeah. It actually has to do with the natural abundance of the isotopes. So the bromine, 79 and 81 isotopes are in a 1:1 natural abundance. The chlorine, what is it, 35 and 37, they're in a 3:1 natural abundance.